the last section of torsional stress that we have to discuss is, I know, your favorite, and probably the most confusing of this class. Whenever we have what I call a static indeterminacy. So again, just the same as axial that we went over 2 weeks ago. You have too many unknowns and not enough equations of equilibrium. And we know the typical equations of equilibrium being like summing x or y, or the moments in the forces in the x, y in direction, and the moments on that member of analysis. So just the same as torsion, where you have loads acting in the longitudinal direction, we can also have too many reactions or unknowns of a shaft going under torsional force. So this is section 5.5, and let me show you a circumstance where it's pretty typical. Now we have a section like a wall, and that wall has a shaft stuck, connected in between the wall. And so if we look at the wall this way, we have two walls, right? Now this shaft has two fixed points. We would say these are fixed. So there's no free rotation like we'd have with like maybe bearings. Like a drive shaft would have bearings on the sides, therefore it's free to rotate when a force is applied. But this is fixed, like say for example on a structural member, or structural member, we'll say that. So now, say that you apply a load T there. That applied load is now going to cause two reactions on the ends. And if we say we have point A, B, and C, we're going to have in the opposite direction TA and TB. So with that, if we draw the free body diagram, or if we sum up the forces now, and let's just say this way is positive. So if we sum the forces and say that direction is positive, we get T minus TA minus TB equals 0. Therefore we get T equals TA plus TB. Now, looking at that, we have one equation and two unknowns, TA and TB being unknown. So, since both ends are fixed, we all know what we need to do next. We need to find the equation of compatibility. Now, compatibility is where we need to find that equation that gives the best representation of how the member under analysis reacts to the applied forces. So, if we have a shaft that has 2 points that are fixed, those 2 points being the ends, we know that the shaft between points A and B is theoretically not deflecting. It may deflect and then come back, but it's not. Ultimately, between A and B, it's not deflecting in a net deflection. So we can say the compatibility for this circumstance is deflection of A and B is 0. Again, no deflection. Sorry, that is axial deflection. We know that the angle of twist between A and B is 0. So, for this case, let's apply the method of sections, and we can see how we can get everything in terms of one variable and ultimately solve for a second equation. Okay, so I'm going to erase all this. So, let's draw the free body diagram. So if we have the free body diagram, we look at, we have TA, T, and TB, right? So we're going to look at sections A, section B. So section A being first, adding up the forces in the positive direction, we get a method of sections that looks like this. TA um, or yeah, TA, sorry, this is AC and BC. And again, if we assume this way is positive, remember, this way is positive, TA is reacting to a positive deformation. So that's why we get a positive reaction to this negative reaction. So again, like I said, positive reactions are a result of a negative torque. So what we do is if we do TA or TAC minus TA equals 0, we know that the internal moment, the internal torque in section AC is equal to the reaction at TA. Simple enough. So now, let's look at section BC. So section BC, we draw the free body diagram. We have TA, and then we have T, and then I'm going to assume that we're going to have direction that way because it's resisting this applied load. So a good, if you don't know the load, I would always assume the opposite direction for the reaction. If you know the load, you might be able to assume correctly and get the right guess. So T, BC. So again, assuming this direction is positive, we're going to get T equals T minus TA minus TBC equals 0. TBC equals T minus TA. Right? Wait. T. Oops, I wrote that wrong on here. Yeah, so it's T minus TA. Okay. So now we pretty much have, knowing that we had this equation, our compatibility equation equals 0, it also equals TAB over LAB over JG plus TBC over LBC over JG, right? So now that is our second equation, and we have everything from our method of sections in terms of TA. So we can pretty much just plug these two internal torques into that equation. So we can get TA times LAB plus T minus TA over LBC over JG, and that equals 0. Pretty much solve for TA, because we have one unknown. We know the lengths, we know the geometry, and if you solve for this, going back to the notes, we can apply that in our free body diagram in our first equation of T equals TA plus TB. Okay, so finally we're going to do example 5.8 in the book. It's pretty straightforward. It's a straightforward compatibility problem for a statically indeterminate member under torsion. So if you look here, we have a member that is 20 millimeters in diameter, and it is fixed at both ends, and it has an applied load 0.2 meters from the end at 800 millimeters, and or 800 newton meters, and then 1.5 meters from that, we have a load of 500 newton meters. So we have two fixed ends. So if we do the free body diagram here, assuming this way, going this way, so the same direction as 800 newton meters is positive. If we do the free body diagram, here, we get, negative TB plus 800 plus or minus 500 minus TA equals 0. So the reason why TA is not opposite of 500 is because you gotta think of it in terms of magnitude. The 800 Newton meters is so high that even though you have another applied 500 Newton meters, there's still a residual 300 Newton meters twisting the member in the same direction as the 800. So your TA is actually reacting to the resultant of 800 minus 500. So they've already done that assumption. But again, if you assume the other direction, you're just going to get a negative value in your answer. So our free body diagram, or our ultimately we have two unknowns. So we get 300 Newton meters equals TA plus TB, right? Pretty straightforward. So now let's just do compatibility. Knowing that these are fixed, we can assume that our compatibility equation from A to B is 0. So if I erase all this, I'm not going to erase this. We have 3 sections to look at. We have section DC, section CB, and section AB. So if we look at section, how do they do it? Yeah, if we look at the first section coming down from the bottom, it's pretty straightforward. So this is section DC. We have TB here, and our internal load here is opposite of TB. We have TDC. If we assume this way is positive, we get TDC minus TB equals 0. So TDC DC equals TB. So that's our first section. So we'll write it over here. So TDC equals TB. Now if we move to TCB, which is the next section, this is CB. So we still have that reaction of TB. Now we have an applied load of 800, and then now 800 Newton meters, and now we have a reaction here to that applied load, and that is TCB. So again, summing up in the positive direction, we get 800 Newton meters minus TCB minus TB equals 0. TCB equals 800 Newton meters minus TB. So we can say here, TCB equals 800 Newton meters minus TB. Now, if we just extend this out a little bit here and add that 300, oops, wrong way, that 500, Newton meters, and then we have a reactionary TAB, we get the same thing. 800 Newton meters minus 500 Newton meters plus TAB minus TB equals 0. So, looks like I made the wrong assumption. TAB that we're solving for ultimately becomes, did I do that right? Oh, sorry, okay, so here's a great example. I made the wrong assumption in the reaction of TAB just because you have the 800 and then the 500, so you still have a residual 300. So the way this is going to be is 300 Newton meter minus TB minus TAB, or equals a negative TAB. So that just goes to show that's the wrong way. So just to avoid that confusion, I'm going to switch this to the right way and this now becomes a negative, and this now becomes a positive, because now I'm adding it to the other side. So again, this is now 300 minus TB because the residual 300 Newton meters subtracted from this 800 Newton meters by that opposite loading 500 Newton meters results in the reaction being the same direction as the 500. So, being said, this now is TAB equals 300 Newton meters minus TB. So, we can erase this, and we have the compatibility equation right there. So that says that TDC times LDC plus TCB times LCB plus TAB times LAB all over the same J over G equals 0. And they're all over the same because it's a constant area and a constant material of this pipe. So pretty much you just plug everything in. So you get TB times LCD plus 800 Newton meter minus TB times LCB plus 300 Newton meter minus TB times LAB all over JG, and solve for TB. I'm not going to do that because I don't have the room. Solve for TB, and ultimately the answer, TB is 645 Newton meter, and TA ultimately becomes a negative 345 Newton meter. So just goes to